Hey, this is Josh. In this video, we'll be going over the Lecture 3 of the Plutus Pioneer program. The theme of Lecture 3 is still about the validator script, but specifically, we're going to take a deeper dive into the script context, which provides metadata information about the transaction, such as who are the inputs, who's the outputs, and so on and so forth. We'll take a look over some of the concepts that was talked about in Lecture 3, and then we'll go over some of the examples that was given. And then finally, I'll go over the homework that was given for this week. So there's a lot of content, so without any delay, let's get started. All right, so the first thing that happened in the Lecture 3 is that we actually had a Plutus update, and there are some things that changed. For example, in the old isData script, we have in our validator script, we had this validator CTX. However, with the new Plutus update, that's no longer the case. We have a new object now that's called script context. And we'll talk a bit more about what script context has and how to find the code and look inside of it. The other big change is, well, not really big, but the other change is that we have some new APIs now. For example, script address over here that actually retrieves the hash of the validator that you give it and then just returns the address directly. So now we no longer have to do what we did in the past and have a validator function, give that validator function to our validator hash to get the hash. And then once we have that hash, we would pass it to the script address function, which then would finally give us the ledger.address that we use. Nothing big, but if you come from lecture 1 or 2 and wondering why your code, specifically the validator CTX, no longer works on the playground, this might be the reason why. So to find the script context, one quick way of looking for its definition is to go to the Plutus Pioneer program repo, and in the README, if you scroll all the way down to the Plutus modules, you'll find a quick link to where the actual code is located at. So we go in here, you can see that we are now in the Plutus repository, specifically in the Plutus Ledger API. And if we scroll down, we see that we have this module, we're importing these things. And then over here, we have data script context. This is the definition of our script context data type. And it's a record. And what script context takes is two data types. It takes a transaction info, which we call the script context transaction info, and the script purpose, which we call the script context purpose. So let's talk about the easy one first. Script purpose is a data type that can be set to be 4 types, essentially. It can either be a minting, it can be spending, it can be rewarding, or it can be a certifying. For the purpose of the lecture, we were told that we are just using spending. Now, what's really interesting is what's inside txinfo. Txinfo is another data, which is a record that contains all of these information over here. Now, all this is some information that will get passed to us in our validator script, including things about our transaction inputs, the fees that the input has to pay, the outputs, and things like that. What's very important for this specific lecture is that we'll be looking at this slot range, this transaction info valid range, and that this gives us a range of when our script is still valid and when we can still do some operations with it. For example, we might want a capability to lock up ADA until a certain amount of time before someone can redeem it, or maybe give a timeline to someone to redeem ADA before it expires. And another one is transaction info signatories, which includes a list of public key hash. Basically, this is just a list of hashes to wallets that was part of this smart contract transaction. And this will be very important to make sure that users are who they say they are. So for those confused about the syntax, let's break it down a bit. A quick recap to understand our script context. So we have a data script context. In Java equivalents, you can think of this just as a class. So we have a public class script context. And then inside script context, we have 2 parameter types that we take in, this transaction info and the script purpose. And so you can think of in our constructor, we just have a variable transaction info that we get that we call script context transaction info. And we also get passed another parameter which is a class called script purpose, which we call script context purpose. We just save this inside our fields, which, Haskell doesn't have fields, but we access them somehow. And that's essentially what script context is. It's just a class that has data. And we dive deeper into that and we see what transaction info is. Transaction info, as you see over here, is basically also a class, which is what we have right here, that takes in all of these parameter types. And so in a Java equivalent, the constructor, which should be called txinfo, not script context, my mistake, would take in the gigantic list of parameters, these parameters specifically, inside this constructor, and then we'll be able to access this information. And then finally, we have our script purpose. It's also a class. It takes advantage of Haskell's ability to combine multiple classes together. I think a quick example is if you're familiar with TypeScript, you might have ran into the concept of union types, where a variable can represent multiple different objects. So we have a script purpose class, and it can either be a minting class, a spending class, a rewarding class, or a certifying class. And what we have to do is essentially whenever we have the script purpose variable, we have to identify what the actual class type is and then extract the information from there. And that's basically what we're looking at in terms of script context. As I alluded to earlier, this transaction info val range, or the slot range data type, is actually very important for this lecture. Specifically, we dive deeper into looking at what slot range is. If we want to find what slot range is, there's a number of ways we can do it. We can actually just find where it belongs. We can see that slot range comes from the Plutus.v1.ledger.slot. So we can go back to v1, go ledger, and then we'll find slot right here, the slot.haskell file. And so here we can find the definition of slot and specifically slot range, which is right here. And if we look at slot range, we can see that slot range is a interval data type that takes in a slot data type. We'll look at what a interval data type is later, but quickly looking at what slot is, we can see that slot is a new type variable. And if you remember from the last lecture, new type basically means take an existing variable like integer, and we'll just call it whatever this new type is. So we're essentially creating a wrapper around our integer and we're calling it slot. Essentially, our slot range is an interval of integers. So what's an interval? Well, if we look up and we find that interval comes from the same file directory. So if we go back and go to ledger, we'll find that there's this interval.haskell script. And we open this. And then we can see that, and we go down here, we'll see that a interval essentially takes in a data type A being our slot. You can kind of think of this as generic. And for interval, it's a record where we have a lower bound and a upper bound. For the purpose of the actual code, you don't really need to know what a lower bound and upper bound is. However, they are defined down here. But essentially, these data type represents a range. And the range will be from our lower bound to our upper bound. And essentially what we're doing is we're giving a lower bound of type A and an upper bound of type A. So in the case of our slot range, we're giving a range of integers. So for example, from 5 to 10. And a quick note in the video, this is inclusive, meaning that 5 and 10, for example, is part of that range. It was mentioned in the lecture that we don't actually create our own interval types. Instead, if we scroll down, we can see that there's these helper functions, such as interval, singleton, from, that generates these intervals for us. And we'll go over some of the examples on a whiteboard. And then there are other things like member and overlap, which we can use to do operations on our interval to see if, for example, if the given value that we're given in this parameter is inside of our interval A. So quick recap, inside our transaction info, we are interested in a transaction info val range, which is a type slot range. And slot range is a interval of slots. And then if you look inside what an interval is, interval takes in a generic type A, and an interval contains two parameters, a lower bound of type A and a upper bound of type A. So in Java terms, an interval you can think of is a class that takes in generics, specifically type T, which can be anything. Not exactly what this is, but specifically lower bound and upper bound is the object that we use that has generics, but I'm simplifying this a bit. So we have a lower bound parameter that's of type t, which in this case is a slot. And if we recall, a slot is essentially a integer. And we also take in a type t of an upper bound. So essentially, we're just creating a interval of ranges. So for example, we have our minimum of 3 and our maximum of 5. And slots come into play for Cardano blockchains. Every block we create, there are slots inside of them, if I understand this correctly. And so as we progress through time, we'll keep generating more blocks in our blockchain ledger, and we'll have more slots in there. So by explicitly stating these numbers, we can write smart code that can make sure that its recipients can validate and claim their Cardano either before or after a specific time has passed in the blockchain. So now to go through some of the helper examples in slot range, let's scroll down a bit. To generate an interval, we have a helper function just called interval, and it takes in 2 parameters of type A, and it returns a interval. And if you look at the definition, all it does is it takes the 2 parameters that you give it, and then it creates an interval data type with a lower bound and upper bound. So this is our prime example of creating an interval of 0 to 10. We call this function with the value 0 and 10, and we get this interval back. Another helper function is something called singleton. We just give it 1 parameter type, and we just create an interval from that range. If we call singleton with a value 5, for example, we would just create an interval of the range 5 to 5. And remember, this is inclusive, so 5 is inside this range. Another example is from, we give this function 1 parameter type, and it creates a interval from the lower bound being the type we give it, and the upper bound being infinite. So this would be, so if we call this function 5, for example, we would get 5, and our upper bound would go to positive infinity. So this is good, for example, if we want to prevent a user from unlocking a script until a certain amount of time has passed. And then the opposite of from, we have 2. With our given parameter type, we create the opposite. We create a interval of negative infinity all the way to our given time. So for example, this can be negative infinity up until 5. As an example, this might be for when you want to give a timeline to someone to redeem their ADA. You have up until slot 5. Well, in reality, it'll be a much larger number in the millions, but you have until some slots in the future to redeem it. Otherwise, the fund is locked from you. So now that we know how to generate some intervals, there are also some nice helper functions that can help us compare intervals or see if a number is within that range. Let's scroll down a bit. 2 example functions that I'm going over is we have a member function, and what this does is given 2 parameter types, A, which is just an integer in this case, in an interval of type A, return true or false if our first parameter A is inside of our interval. And so that this can be something like, let's say 3 and then 1, and then we're given a range of 1 to 5. Now I won't go into the details of this. It seems like what it does is it generates a interval of our value 3 and then see if there's some sort of overlap between these 2 types. But the implementation detail is not important to us. The important part is this returns true because 3 is part of the interval 1 through 5. And another example is overlap. We're given 2 intervals. So let's say 1, 5 and 3, 7. And all we want to do is to see if these 2 intervals have any overlapping numbers. So once again, also without diving into the code, this will return true because this shares 3, 4, and 5. And so these are some of the helper functions that you can use by looking at the interval class. I highly recommend just kind of looking over the implementation of intervals and slot ranges to figure out how the code works. Worst case scenario, you'll learn more about the library and how Haskell works. So not a bad trade-off. So unfortunately, the interval functions require actual code to run. So a quick way to be able to play with the interval functions, besides going to the playground itself, is you can use the interactive CLI that comes with Haskell. So one way you can do it is go back into your virtual machine, make sure you actually update everything, do a git pull command in both your Plutus and Plutus Pioneer program. I already did that, so we don't have to do it. And then go inside your Plutus repository, run nix-shell to get a virtual environment that has Haskell and Cabal installed. And then once you have that, go back and go to the Plutus playground or Plutus Pioneer program, go inside code, go inside week 3, and just run cabal repl, and this will build your week 3 repository and you'll give you a CLI, which you can see on this specific thread. So once you have the interactive environment running, the first thing we want to do if you want to play with the interval module is to import it. So that's import Plutus v1 ledger.interval. And I already did it, but this will add this string. So now that we've imported this function, we can do a lot of things. Now we can, for example, call the from function. So let's say we have a type A and we say from 5. Well, okay, I already made it A, so let's say B. And then if we want to see what B is, we just type B, and we can see that B is a interval that has a lower bound of 5, which is what we defined, and it has the upper bound of infinity. And so this is just a neat way for you to quickly play around with the code and see what happens. So that being said, let's look at the example code that was talked about in the lecture. To go over the exercise that was talked about in lecture 3, I'm going to use the community Plutus playground, which you can find linked in the Plutus Pioneer program. The first example, if we pull back into the code in week 3, is vesting. And so we'll just copy and paste the code in the asking.that haskell file, and then paste it in the Plutus playground. Let me compile this first. All right, so on the high level, vesting is a smart contract that allows you to give a certain amount of Cardano to another wallet. And there's a specific timeline that we have to wait before the second wallet can redeem it. So for example, we can say 10, or let's say 5. So we have to wait 5 slots before anyone can redeem it, and we can redeem 100 Lovelaces. We have to wait, let's say 5 blocks, and then wallet 2 can grab it. And of course, we should update our Lovelaces. Let's make this 1,000. And then after we do that, we have to wait again. And so the first problem is we don't know what the pub key hash is of wallet 2. And what was done in the lecture was we went to the CLI and then we called some helper functions to find the wallet, but there's an easier way. So I'm just going to hit evaluate, and we'll just keep the string empty for now. And I'll show you how we can grab the address. All right, so now that we're here, we have our output. We can now see what our pub key hash is for wallet 2. So we just click the clipboard on the side, and now we have access to that. But just a quick preview, we see that we were able to successfully lock up the 100 ADA. One thing you might know is that we have 890 locked up and 700. And if we look at slot 1 transaction 0, one big change that happened in lecture 3 of this new Plutus update is that now fees are taken into account. So whenever we make a transaction, we have to also now ensure that we have enough Lovelace to cover the fees. Anyways, so back to the code. We close this, and now if we just enter the code that we just copy and pasted, and we try again, we'll now be able to actually successfully grab the locked up ADA. Right, and we scroll down, we can see that now indeed wallet 2 has 1,090 ADA. Now let's dive into the actual code. The magic of all of this is inside our validator script, and everything that the lecture talked about at this point, this builds up to this logic that we're building. Specifically, how do we check time in our script before we decide to release ADA or not? That's all inside the script context, specifically inside this text info valid range. So how we read this validation script is, if you recall, a validation script takes in 3 parameters. It takes a datum, it sends in a redeemer, and then finally we have script context, which provides information about the transaction, which is the key to this whole entire lecture and how we find the slot ranges and our pub hash keys. So the first thing is we look at vesting datum. For those who remember lecture 2 where there was a myStl redeemer, we do something very similar. We create a new data type called vesting datum, which is a record. And this vesting datum has 2 parameters it takes in, a pub key hash, which is basically your wallet address, and the slot, the deadline slot, which is how long we are waiting for. And so to make our vesting datum work for our validator script, we need to use something called Plutus tx.unstable make is data. And what this basically does, it tells the compiler to change the vesting datum to also inherit the is data type, so we can use it on the validator script essentially. Now that we know what the vesting datum is, we look at the actual implementation of the code, starting from line 43. So we define our 3 types. We call our vesting datum dat. Our redeemer is a unit, so it's essentially just void. It doesn't do anything. And we call our script context ctx. And in the actual code itself, we do 2 things. We do a trace if false. We give the message of a failure, and we call a function we can define called check signature. And if this returns false, we would send this message. Otherwise, everything looks good, and we continue. We combine this function, this line of code that we wrote, with a AND logic, which also has its own trace if false, and we run a function called check deadline, which is where we check to see if we've passed the deadline. And if that returns true, then everything is great, and both of these would evaluate to true. And then at this point, it's just a comparison. True and true is true. Likewise, if either of them is false, true ANDed with false becomes false. So we will not unlock our ADA. So that's what all this function does. It just evaluates 2 functions and then AND them together to see if we should unlock the funds or not. So the first thing we do is we do a check sig, which if we look in this where keyword, which allows us to define inline functions. If we look at check sig, we can see that it's a function that just returns a Boolean. And what this does is, this is a bit hard to read, but this syntax is we are getting the beneficiary data of the vesting datum. And we're calling the element function, which after looking it up is essentially just a function to see if the given data, which in this case is our beneficiary, which is a pub key hash, is within a list of pub key hashes. So this was confusing for me to understand what's happening at first too, but what's essentially happening is this is actually the same thing as this dat beneficiary. We first call info, which returns us this transaction info object. And we do that by grabbing our script context and then returning the script context transaction info that was passed in as one of our record parameter types, which you can see here. And then once we have that transaction info object, we grab one of its parameters, which is the transaction info signatories, which is a list of pub key hash keys. And so what we're essentially doing here is we're saying, is the beneficiary, is this pub key hash inside this list of pub key hashes? Another funky thing is that this syntax here, where we have the keyword elem, this is mostly just for a readability standpoint, but this is equivalent to is basically saying elem of the beneficiary inside our datum, and the second parameter would be our list of pub key hashes. And so this is equivalent. And this is how we check our first script to see if and this is how we check to see when we are redeeming with our second wallet, wallet 2, to see that the transaction that wallet 2 sends out, if the beneficiary that wallet 1 specified is in that list of that transaction from wallet 2. And so this code is executed when wallet 2 sends its redeemer function, which is to grab the data. which we get from grabbing this specific parameter type, we would have a list of transactions which includes the address of wallet 2. And then because in our vesting data, wallet 1 specified wallet 2 as the beneficiary, we're just checking to see if our beneficiary is one of the hash keys inside our list of people writing this transaction, which in this instance is just wallet 2. And so that's how we do check signature. The next function we wrote is check deadline to make sure that we've waited enough time. And if we look at that definition, check deadline just returns a Boolean. And if we look at the implementation, we're calling from, and this is our interval function. And from creates an interval from the number that we're given, which let's say is 10, all the way to infinity. And then our datum, which is our dat, specifies our deadline value, which, as you might recall, is a slot. And so we're using the contains function that was provided in the interval module, and we're checking to see if the deadline that our wallet 1 set when they decide to give their ADA in this contract, we want to check if that deadline is currently inside the range of our script context. And so this would probably just be some time from negative infinity, I assume, up until the current time that the Cardano blockchain is at. So let's say current is 15. When we run this code, if 10 is inside this range, if 10 to infinity is within the range of negative 10 to current, which is 15, it will return true. And 10 is indeed inside of this range, so this whole function would return true, which then would unlock the data. And this is how we were able to use script context. And the rest of the data is basically boilerplate. We first need to set up our vesting type, which includes the redeemer and datum that we need to send to our validator script. And so our datum type is the vesting datum, and our redeemer type is just a unit. And then we need to create an instance of the code using template haskell. This is essentially just copy and paste. We give it our validator script. We define the data types that we're passing in. And with that instance, we create a validator data type, which then we would use to get the address of the script itself. And that is where we send our transaction information to. The lecture did go over some of the wallet, but since that's not the core focus of week 3, I'm just going to skip it and just assume everything over there is correct. But more or less, this is how we use the script context. In example 2, we're going to look at the parameterized Haskell script, which is located here. Just copy all of this, go to the Plutus playground, and paste. So if we look at the validator script, we'll see that it's changed a bit. Normally we accept 3 parameters, our datum, redeemer, and our script context, and return a Boolean. Now we have this extra vesting param. So what's a vesting param? If we look up, we see that vesting param is actually the same as the vesting datum that we had earlier. We have a beneficiary, that's a pub key hash, and then we have a deadline, that's a slot. And if we see the implementation of our validator script, we see that we have P, which represents our vesting param, and that we're doing the exact same thing as we had when we had a dat for our datum, which is now just a unit. We just grab the beneficiary value from our P, and we grab the deadline value from our P. So the code is exactly the same. So what exactly is this vesting param and specifically parameterization? In the lecture, parameterization essentially is just a way for us to create a different instance of a validator script. And what I mean by a different instance, I mean that the script would have a different address for each vesting param. And how this can be relevant is in the past before, we had one smart contract with these 3 parameters, and it has one address. So as long as the wallet has access to the address of that smart address, any wallet can be part of it. And we will only have one instance of our smart contract. By defining a vesting param, we can pass in custom data that will generate a new instance of our validator script. So now we can have 2 smart contracts. Maybe one would be for Bill and Jan, and then maybe another one can be for Bill and Bob, for example. what this means now is previously we would only have one instance of our smart contract, and that would be only for Bill and Jan, and then no one else can use the smart contract. However, now because we have a vesting param and we parameterize our validator script, now we can have multiple different users create their own instance of this same smart contract and then lock up funds for someone else in the future to redeem. We already went through the implementation. It's exactly the same as example 1. However, the interesting part now is seeing how to use parameterization in the rest of our script. Primarily, this is inside our template Haskell code. As you can see, our vesting data type, we no longer have a datum type anymore. Now it's just a unit. And the lecture 3 itself goes into a lot greater details about creating our instance. But what we need to know is to apply the new parameter that we received, that we're receiving in our validator script, we need to update our validator script to take in a parameter. And I won't go into the detail of this. You can watch the actual lecture 3 video, but this is basic copy and paste boilerplate code. It will be the same pattern every single time, so don't worry if you don't understand what's happening, because quite frankly, I don't either. Now that we have our instance function that defined that creates our script instance, we actually need to use it to generate an address. So we look inside this validator function that we had, notice that we also pass in this vesting param, and then we still return the validator object. And inside the implementation itself, you notice that we actually never use the vesting param, but that's because of this composite function, which is this dot right here. Essentially, what this is doing is it's taking the parameter that we get, which is vesting param, and we are calling instance of, let's say, P. And so what this does is the composite function would take the parameter, call instance, and pass in the P type, which is what we have over here. We're passing in P into our instant function. And then with the return type, which over here is the script.instance, we would pass it in to our script.validator script function. So if we were to write this out in Java, the implementation would be something like, we would just call validator script, and this function takes in an instance. So we call this instant class, which then we pass our p param, which is our vesting param. And then with that return type, we pass it into our validator script. And if we scroll down and look inside our source address, and this is where we get the address to our smart contract, we do the exact same thing. All right, so for homework 1, we go to the homework 1 that Haskell file, copy everything, go to Plutus Playground, and paste. And so for the homework 1 assignment, the goal is to implement this validator script, and the implementation is that we should validate if either beneficiary 1 has signed the transaction and the current slot is before or at the deadline, or if beneficiary 2 has signed the transaction and the deadline has passed. So if you watch the video, you'll know that beneficiary 1 is the person that you are dedicating, that you are allocating the ADA to, so person you are giving to, and they have until the deadline to redeem it. Otherwise, beneficiary 2, which is the person who sent the vesting datum to start with, person who initiated, sent the datum, can take the ADA back. Specifically, they take it back after the deadline has passed. To implement homework 1, this is actually very similar to our vesting code. We just need to change around the logic a bit. So to save time, I'm going to go back, go to vesting, and inside our validator script, we're just going to copy and paste these helper functions that was defined in the lecture. And I'll just paste it. And so a quick recap, we have 3 helper function: info, which essentially get the tx info of our script context, and we use this later inside our check deadline to get a list of valid ranges, and so which goes basically from the beginning of time up until the current time that we are at right now. And then we have check sig, which grabs our context and it gets a list of pubkey hash that is associated with the transaction that is being made. And in the original code, we give the vesting datum, and then we just check the beneficiary to see if its pubkey hash is inside our list of hashes for that transaction. And then we have our check deadline code, which allows us to get the time range for our transaction. And we just check to see if the specified timeline from our datum is within this range. If it's within this range, that means that time has passed the deadline. So remember that, that's important. So the first thing in our implementation is we need to define our types. So we have dat and ctx. And so now we need to actually implement the code. So I'm going to use something called guard. So I'll just get rid of the equals false. And I'll just put a pipeline here. And the first thing I want to do is to check if our deadline has passed. And so we'll call our check deadline function and we'll give it true. And remember, if check deadline returns true, that means that we have passed the deadline period. And if we have passed the deadline period, that means beneficiary 2 can now redeem their ADA back. So that returns true. Then we'll just call trace if false, and our message would be this isn't beneficiary 2. So we're going to call check sig. And right now we need to update check sig, because right now check sig would always call the beneficiary of our datum, which is actually in this instance, this code wouldn't even compile because we no longer have a beneficiary type. We can't just change this to beneficiary 1 because, for example, what happens when we need to check if beneficiary 2 exists? So instead, what we have to do is we need to update our checksig function to take in a pubkey hash instead, and we'll just pass that into this function, and then we'll just check if that hash is inside of our transaction list. So to do that, we can just do pubkey hash. And so to define our type, we'll just call it p. And then we'll just replace taking the value from our datum and just use p and see if this specific pubkey hash that we passed in is inside the list of pubkey hashes for this transaction. And that's it. So now we call checksig. We just need to use our datum and we just pass in the beneficiary 2 address. And so if this function returns true, we unlock the funds and the original sender gets their ADA back. And if it's false, we just print out a message that says this isn't beneficiary 2. In the next case is what happens if our check deadline function returns false. And I'll just call otherwise because there's really no other case. We'll do the exact same thing, except the opposite. So instead of checking for beneficiary 2, we check to see if this is beneficiary 1. And we just call beneficiary 1 of our datum object. And that should be it. Let's compile our code and see how we do. Yes. It doesn't like the fact that I'm calling these. It doesn't understand the ordering of the code, so I need to wrap the checksig inside parentheses. So this will evaluate to true or false first. Okay, there we go. All right, so simulate. Let's put 1000 for everybody. And so the first thing we need to do is we need to get the address of wallet 2. So I'm just going to put in something random. I'll put in, let's say 5 for our slot and 1008 ADA. All right, let's grab our wallet 2 address. Let's close this. And now we just say, let's wait for 3 blocks. And then wallet 2 wants to grab. And we paste in our wallet 2 address in our get function as the beneficiary. Let's wait, and then let's evaluate. This will probably fail because, yeah, this will definitely fail because I put in 1000 Lovelaces. which is above the threshold of how much we allocated. So let's go back and let's put 100 and let's try again. All right, so looking at the end result, we can see that this works. Wallet 2 now has the 90 ADA and wallet 1 has 890. So we have successfully locked up and retrieved it. So let's go back. And let's say instead of wallet 2 grabbing it, let's say we wait 6 and we pass that deadline. And now wallet 1 wants to grab it. We evaluate and wallet 1 should be able to get their ADA back. Okay, we scroll down and we see that's indeed what happened. Wallet 1 now has 980 because we burned 10 lovelays locking up the 100 ADA and then 10 lovelays getting the original locked up value back. So that's homework 1. Now to homework 2. Do the same thing. Open our homework2.haskell file, copy the code, and paste. Homework 2 is all about parameterization. If you look at our validator script, we'll see that we have a new parameterized function called pubkey hash, and our datum is slot. We don't get anything for redeemer, and we still have our script context. We also need to note that we now also need to implement a instance validator and source address using the given pubkey hash as the parameter type. It turned out that I completely overcomplicated the problem. This is very similar to just the first example in this lecture. We just specify one person we want to give the ADA to, and they can only unlock it after the deadline that we pass, which is our datum, has passed. And that's it. And so let's implement this. I'm going to call our pubkey hash P, and then our slot I'll just call S, and then our script context will just be CDX. So the implementation of this is very similar to our other code. So I'm going to, for the sake of time, go back and go to vesting. And once again, I'll just copy and paste these helper functions. In fact, I'll just copy and paste this whole thing. That's how similar it is. So the only difference now is instead of getting a datum, a vesting datum that has a beneficiary parameter and deadline, we just call it separately now. So instead of the beneficiary in our check sig, we just use the P that we're given inside our script instance. And then instead of calling the deadline parameter from our datum, we just give it the slot that we received instead. And that's actually all we need to do to implement our validator script with a parameterized pubkey hash. Now, the next part is we need to implement the template Haskell code. And this is mostly just a lesson in copy and paste. And so I'll just go back to this parameterize.hs. And then I'll just copy and paste this code and implement it. So the first thing we need to do is we want to make sure that our instance is the same. And that's it. Well, actually, we do need to update our datum to be a slot. And so that's that. And so the next part is we need to use our validator, and we need to pass in the pubkey hash to our instance. And we do this by just relying on that composite function that we've talked about previously already. And likewise in the source address. And that's it for homework 2. So I'll just compile this code. And there's a duplicate instance, and that's probably because if I move this down, yes, I will have to delete this. All right, let's try again. All right, it compiled. Now I'm going to simulate. Right, copy, and then we paste this back in. And now let's say we wait 5 blocks, and then wall 2, or actually no, we need to wait at least 10 blocks. Then we need to grab wall 2, wait again, and evaluate. Because remember, in this example, it's similar to our first and second example that went through this lecture. Wall 2 can only redeem after the deadline has passed. All right, so if we look at the transaction results, we can see that that does happen. Wallet 2 has now 98. And likewise, if we try one more time and we try to redeem it at, let's say, slot 5, we'll see that this will fail. All right, if we scroll down, we can see that Wallet 2 has yet to redeem that 100 ADA. And so that's it for homework 2. Hopefully this has been helpful, and if you have any questions, do leave them in the comments below. I try to get to them as whenever I see them.